Okay, so we're starting with the next material. It's a continuation of the, the material we just covered. We will be using chemical formulas and chemical names all the way through this, and you're going to have to be able to um, do this without notes and in the internet. Ultimately, just like when this is not an online class. So next thing we're going to do is we're going to apply the chemical names and formulas to how what they are used for, and that's chemical reactions. And a chemical reaction is the process of making or breaking pure substances from another pure substance. For instance, burning paper. Uh, Paper, which is basically glucose, and if you're taking 111, you'll learn about that. Paper, when it's exposed to air in the presence of a spark, it ignites and it goes kaboom, and carbon dioxide and water are released. So, glucose and oxygen were the original substances, and after the reaction, we have two new pure substances, carbon dioxide, which are different in character, physically and chemically, than glucose and oxygen. So we want to explore uh, the relationship between. So let's rewrite the burning of paper. Okay, here you go. Here's a diagram: burning paper. So burning paper is basically glucose. It's added with oxygen, and it yields. That means gives, makes carbon dioxide and water. Okay, so shortness. Okay, instead of using the words added with and yield, we're going to use a plus and we're going to use an arrow here. So glucose added. This doesn't mean like plus. I mean, doesn't like uh, it, it's combined with. Okay, so glucose is chemically combined with oxygen, and it yields carbon dioxide and a other new product, water. Okay, so here's a word equation, and then we also want to be able to describe it in terms of the chemical equation. And from our understanding of names and formulas, you know the formula for glucose is C6H12O6. Formula for oxygen is O2. Formula for carbon dioxide is CO2, and water. So we can write initial chemical equation for this reaction. Okay. Now a big concern of this is energy. We know that this reaction produces a lot of heat. Okay, burning paper, burning wood, etc. And heat is a type of energy, and thus it really should be part of the reaction on this reaction statement. So we should really say glucose added to oxygen, chemically added to oxygen, will yield carbon dioxide and water and heat. Okay, so or we can write it with the chemical formula be C6O12O6 plus O2, CO2 plus H2O plus heat. And how about the spark? Well, we can put that in equation too. We just put it over here because really the spark just comes and goes. It doesn't really it's not part of the reaction itself. So you have glucose plus oxygen with a little spark, carbon dioxide, water, and heat. Or chemically, you can write it like this. Okay. But for now, what we're going to do is we're going to leave off the heat and the spark and just look at the pure substance that we started out with, and the pure substance we ended up with. Though the heat is very important. Okay, so to generalize, every chemical reaction starts with reactants. That's our beginning stuff. Ends with products. So there's a general word in chemical equation. So from this up here, we'd say the reactant yields product, or you could just say reactant aero product. And the chemical equation would be R with all its symbols going to P. Okay, and we're going to be using both of these. We'll have a word equation for a chemical reaction, and then we'll have a chemical equation. All right, so we're going to go over a few of the most basic chemical reactions. There's combustion, single replacement, and there'll be two type. And then there's something called double replacement, two type. And if you notice, these two guys both have replacement, so there must be similarities between the two. All right, so what we're going to do is let's get started, and we're going to start with combustion. Okay, you all probably have heard of combustion. It is probably the most common reaction that we encounter in our daily lives. When we drive our cars, we combust the gasoline, and that moves our cars. If we heat our house or cook with propane, okay, this is combustion. And of course, burning paper, I just said, is combustion. And heck, we're even combustion. So here's a picture of, I guess, of somebody combusting. There's this thing called spontaneous combustion, which is kind of a myth. People just kind of catch on fire. That's impossible. All right. But anyways, so why do we do this type of reaction? Well, why? So what's important? Why do we use this reaction here? Why is it, for gasoline and so forth? Because it gives off a lot of heat. Okay, it's simple. Combustion gives off energy to heat our houses, to move our cars, to move our bodies, to cook our food, etc. What we're going to do is just look at the combustion of alkanes. And so we'll have a word equation and then a chemical equation. And the chemical equation will look like this. We'll have our alkane, and then what's going to be the same between, for all the word equations, will be the whatever the alkane is, and then this will not change. Plus oxygen yields carbon dioxide and water. The chemical equation will be whatever the chemical formula of the alkane is, and then this. These two things here will not change in terms of the substances. Okay, so don't make something up. It's just simple. It's the alkane, right? Oxygen, carbon dioxide, and water. Okay, we'll go over several, quite a few examples of this. So let's get started with combustion of natural gas. This reaction is used at power plants. Okay, so I don't know if you ever driven by a distillery, and you will notice is that there's a flame coming out of the, there's always flames shooting out at the top. So this is natural gas that's being burned. Okay, and there's reasons for that, but it's not what I'm going to talk about now. Okay, and so natural gas is methane, and what they do is they combine it with oxygen. So they pump natural gas into a power plant. They pump in air, and they spark it, and it produces carbon dioxide, gas, and water vapor, which is a gas. These two gases that are released, the carbon dioxide and water, it's a lot of pressure being created from the gas. What these do is they cause some giant fans or turbines to turn. Okay, the turbines are wrapped in copper wire that surrounds a magnet, and as the turbine turns, because of the gas, the copper wire turns about the magnet, and this creates electricity. And the electricity is sent along the power plants to our houses to keep our computers running and our refrigerators. Okay, I just want to show you that this is a practical use here of this type of reaction. So let's take a look at the actual chemical reaction. Right, so what we do is we have our alkane, and then the thing that doesn't change. So it's methane plus oxygen yields carbon dioxide and water. The chemical equation is our alkane plus and the thing that doesn't change. All right, and it's right there. Okay, and this is the initial chemical equation. So you have your word equation and chemical equation. So the idea is for this type of reaction, I would say write the word equation for the combustion of methane. And so you write this out and write the chemical equation for the combustion of methane, and you write that. Okay, so let's take a look at this a little bit closer, the chemical equation. And so let's count the number of atoms on each side. So there's one carbon here and one carbon here. So there's one carbon in the beginning and one carbon when we're done. Good. Number of hydrogens, there's 4. So this 4 means 4 hydrogens. And there's 2 over here. 2. And the oxygens, we have 2 oxygens here. And we have 1, 2 over here, and 3. So we have 1, 2. So we have a total of 3 oxygens on the product side, okay? Right, notice that there are not the same amount of oxygen and hydrogens on each side. It looks like 2 atoms of hydrogen have disappeared, have gone 4 to 2, and 1 hydrogen atom has appeared out of nowhere, and the product has gone from 2 to 3. Now, you might be thinking that 2 hydrogens turn into 1 oxygen. No, sorry, that doesn't happen. Elements don't turn into other elements. That's really hard to do. Well, we decided 100 years ago that elements just can't appear and disappear out of nowhere. Okay, this was brought forth by a guy named Lavoisier. Those elements are always there, we're assuming, okay? So right now we're assuming the amount of oxygens on this planet are the same as there was 1,000,000 years ago, okay? And the amount of carbons are, and so forth. In fact, we think this is a universal law. And what we say is that it's called law of conservation of matter or mass, is that the matter or mass, because matter has mass, cannot be created or destroyed, but only can be transformed. So you just can't create oxygens and hydrogens, destroy them in midair, and like Harry Potter and magic, okay? It's not like that. They used to think that. I mean, 250 years ago, even 100 years ago, they used to think that these kind of things would happen. So this law says something is wrong with our chemical equation, right? So you have to ask, is the chemical equation totally wrong? Or can we just adjust it and fix it? Well, we know that this is the reaction. We know that when we add methane to oxygen, it produces carbon dioxide and water. So it's not totally wrong. So that means we must fix it. Okay, so when I first took chemistry, oh boy, I can't believe it. I did a lot of dumb things, okay? I said this was real easy. I have this, carbon dioxide and water, and I'll fix it, okay? Here's the 2 here. Heck, I'll just change it to 3. Now there's 3 oxygens on both sides. And heck, there's 4 hydrogens over here. I'll just put a 4 over here, and I'm all done. Haha, voila. That means, ta-da, I done it. Okay, no, you can't do that, because O3 is not O2, oxygen, and H4O is surely not water. I can't change the substances. I can't change them once I put them in the equation. It has to be CH4, O2, CO2, and H2O. Okay, I have to leave the subscripts alone. All right, I just have to, okay? So what do I do? So that's the next thing. So what else can I do? Well, how about if I can change the amount of substance on each side so that somehow the elements will come equal? Okay, well, this is what we do. And what we do is we will put a coefficient in front of the the molecule, like CO2, which means I have 2 carbon dioxide, which also means I have 2 carbons and 4 oxygens. Okay. And this is really the important thing here. Okay, and this, what we're going to do is we're going to use this tool right here by putting this thing called coefficients, and you've heard of coefficients in math. What it'll do is balance the equation. So systematically, we'll be adding substances in terms of numbers to each side so that we can get the same amount of elements on each side. And we'll go through that process. Okay, there are many ways to do these. Now, if you've taken chemistry before, you might have one way, done it the way that your teacher did. I do it my own way, but you get the same answer. I'm going to show you a way to do balanced equations for combustion reactions. It won't work for any other type of reactions, though it could. There's no reason why it can't. If you think about it, okay? So these things are not automatic. There's not like a plug-in thing. You have to think about it. But it really works really well with combustion reactions. So make sure you follow along to what I'm doing exactly, okay? Don't go off on a tangent and try to figure it out on your own. I mean, it's great if you do. If you've come up with your own way of doing it, that's fine. But I'd like you to try to stick with me on how to do this. All right, so we're given a chemical formula, CH4 plus O2 plus C2H2. Now, first thing we're going to do is put a 1 in front of the methane. So we always put a 1 in front of the alkane. All right. Okay. And then what we do is we count the number of, so we have 1 carbon here. All right. And then what we notice is that we want to have 1 carbon over here. So what we do is put a 1 in front of it. Okay. So now I put a 1 in front of the carbon. Now I have 1 carbon on both sides. So what this means is this coefficient is 1, and then the subscript is also 1. So 1 times 1 has to equal 1 times 1. Right, next thing we'll do is count the hydrogens. So always put a 1 in front of the alkane. So now I have 1 times 4. I have 4 hydrogens on reactant side. All right. Okay. Now, over here on the product side, I have 2 right here. So what number times 2 will give me 4? Okay. Hopefully you'll see that just simply 2. Okay. So this becomes 2. So now we go to product side. There are 4 on the left side. There's 4 hydrogens. We need to have 4 on the product side. And then you can see that X times 2 has to equal 4. So it's going to be coefficient times subscript is how many of the atom. Okay. Right, we're not done. We're done with the carbons and the hydrogens. They've been balanced. There's one carbon on both sides and there's 4 hydrogens on both sides. But now we gotta check the oxygens. Okay. So what we're gonna do is we're gonna go to the product side and count the number of oxygens. So the first two things we did, we counted the carbons and hydrogens on the product side and fixed them. On the reactant side and fixed them on the product side. For oxygens, the opposite. Okay, oxygen is opposite. So we're going to start for the product side and go to the reactant. All right, so you got to count the number of oxygens on the product side. Again, the number of atom types are the coefficient times the subscript. So for carbon dioxide, it's 1 times 2 oxygens. So there's 2 oxygens in carbon dioxide. And for water, there's 2 times 1 oxygen. And so you have 4 oxygens on the product side. Okay, so what I have is some y times 2 has to equal 4. So y times 2 equals 4, where y is the coefficient of O2. So simple algebra will tell you that, divide both sides by 2 and you get 2 as your number to put in front of here. A real simple way to do this is once you count the number of oxygens on the product side, you just divide by 2. Okay, and that'll happen all the time. So all you do is you count up 4 oxygens. 1 times 2 is 2. 2 times 1 is 2. Okay, so there's 4 oxygens. Divide by 2 is 2. And put that in front of the oxygen. That's all there is. Okay, so let's see if it works out. So I have 1 carbon on both sides. How many hydrogens I have? 1 times 4. And 2 times 2 is 4. And I have 2 times 2, 4 oxygens. And then I have 1 times 2 is 2. And 2 times 1 is 2. And so I have 4. And voila, I'm done. Bingo. So let's do some more, so you can follow through, see how it works. Okay, so let's do another one. Let's do the combustion of pentane. So first thing we want to do is the word equation. So it's simply pentane plus our unchanging part. And then the chemical formula, equation, pentane, and again our unchanging part. Okay, so what we want to do is balance this equation now, because it's not balanced. I have 5 carbons over here and 1 over here and so forth. So first thing is put a 1 in front of the pentane. Now I put a y and an x over here as the unknowns. Okay, so I have 1 times 5 carbons over here. So I have to put a 5 over here because 5 times 1 is 5. So my carbons are all set. Okay. Now let's do the hydrogens. So on the reactant side, so both carbon and hydrogen, we check the reactant side and fix the product side. We count the number of hydrogens. So it's 1 times 12 is 12. Now you need to have the same amount over on the product side. So you have 2 here. So x times 2 has to equal 12. So what number here times 2 is 12? Well, it's 6. So I put here. So I have my carbons and my hydrogens. So the next thing you do is you count up the number of oxygens. Right? So now on the product side. So we have 5 times 2 is 10. And 6 times 1. Add them together. You have 16 oxygens on the product side. Okay. Now I just said divide this by 2. It's just simple. Divide it by 2 and put that number in front here. And you're done. And if you count them up, that's what you get. So there's 5 carbons here, 5 carbons here, 5 times 1. 12 hydrogens, 1 times 12, 6 times 2. Number of oxygens, 8 times 2, and is equal to 5 times 2 plus 6 times 1. Okay, and you're done. Combustion of propane. Again, do the word equation, put propane, and finish off. Okay, one thing I want to make sure you understand is, notice in this one I put water plus carbon dioxide. And I think there's a rule in math that's called the associative rule or something that says, 1 plus 3 is equal to 3 plus 1. Okay, so I typically put them in certain orders, but they don't have to be. So it could be oxygen plus propane, and so forth. I know I used to get stuck on that. I did whatever the teacher did, and for some reason I thought that was more important than understanding it. Okay, so the unbalanced equation. Here's propane, and here's the part that always stays the same. So I'm going to balance the equation, so I'm going to put a 1 in front of my alkane, and then 1 times 3 is 3, so I put a 3 in front of my carbon dioxide. Okay, so my carbon dioxide is fixed. Now I want to fix my hydrogen, so I count how many hydrogens I have on the left side. 1 times 8 is 8. Okay, what times 2 is 8? Well, 4 times 2 is 8. That's what I have here. X times 2 has to equal 1 times 8. And then you go the other way, count how many oxygens are on the product side. You have 4 times 1 is 4. And then 3 times 2 is 6. So there's 10 on the product side. Divide by 2 equals 5. And put that number from the O2, and it's automatic. Bingo. Okay. So the key thing is, don't worry about trying to do the math. The idea is, it should make sense. Okay, I say do it quick but slow. I mean, think through it. But you don't have to say 2x equals 10. Okay, all right. You should just notice is that what you need to do to multiply to get one number to get the other. And we're always going to use big numbers that are going to be fairly simple to use. So remember, the way we've done it is put 1 in front of the alkane, then count the number of carbons, and then put whatever that number is, put that number in front of the carbons. So, for instance, like the last one we had was C5H12. Put 1 in there, count the carbons as 1 times 5, and then, so it's 1 times 5, and that'll go in front of the CO2. Okay, count the number of hydrogens on the left. So 1 times 12 is 12. Well, if you divide by 2, that's be how many waters? Because you have 6 times 2 is 12. So simply, if you just count up the number of hydrogens on the left, divide by 2, that'll be your number on the other side. And as For oxygen, it's the same way. You count up the oxygens on the right, divide them by 2, and put it in front of the H2. Okay. So for hydrogen and oxygen, you just count up the total and divide by 2. So let's do another one, heptane. So here's the word equation. And here's the initial chemical equation. All right. So put a 1 in front of the, and this says I have 7 carbons, so I'm going to put a 7 in front of the CO2. Done. Okay. So now I figure out how many hydrogens. I have 1 times 16, which is 16, divide 16 by 2, which is 8. Put that in front of the water. Now, how many oxygens you have? 7 times 2 is 14. 8 times 1 is 8. 14 plus 8 equals 22. Divide by 2 is 11. And that goes in front of the O2. There you go. So it's simple. Okay. Simple pattern here. Remember, this will only work for combustion of alkanes. Alright, so now we're going to do the same thing with butane. And I'm going to do exactly what I did before. Okay, not going to deviate. I'm not going to think too much. I'm going to just turn into a robot here. Okay, so butane, that part, butane, chemical formula. Okay, put a 1 in front of the butane, count the number of carbons. So put 1 here, 1 times 4, put a 4, done. Right, count the number of hydrogens on the left. 1 times 10 is 10, divided by 2, 5. All right. Okay, so I'm done with my hydrogens and oxygen. Now I count the number of oxygens on the right side. So it's 4 times 2, 8. 5 times 1 is 5. Now, divide by 2, 6.5. Wait a sec. How can I have a 6.5? How can there be 6.5 O2s? Does that mean, what is the heck is a half of O2? Isn't a half of O2 an O? I'm really confused. Okay, so this is a typical thing with students when I do this in my class. And I say, just do what I say. Just do exactly. And they go, well, it doesn't make sense. How can I have a half? Just do it, and you'll see why. So let's write it out. Does it work? All right, so here's what you have. Just does it work? Don't think about it. Did it work? So you have 1 times 4 is 4. 4 times 1 is 4. 1 times 10 is 5 times 2. And then 6.5 times 2 is 13. 4 times 2 is 8. Plus 5, 13. It works. Okay? So what's going on? How can you have a half of O2? Okay, well, let's talk about that. Okay, there you go. How can you have a O2? Half of O2. Ache. Okay. Okay, the issue is big versus little. When we do chemical reactions, we're usually using trillions and trillions and even more than trillions and trillions, like trillions of molecules, and not just 1 or 2 molecules, or even 15, okay? So here's a question. Since what is a half of 13 million? 6.5. Okay, so you can have 6.5 million, but I know you can't have, if I said have 6.5 things, that doesn't make sense, okay? So the coefficients that we use really are represent ratio numbers of one substance compared to another. So when I say 6.5, I really mean there's 6.5 times as many as maybe another. So if you think about it, if I have 1 million CH4s, I will need 6.5 million O2s. And that's what it really means. So it says quantities. It says one quantity of CH4, C4H10, plus 6.5 quantities of O2 will yield 4 quantities of CO2 plus 5 quantities of H2. And they're not individual things, they're quantities. So this be like a million, trillion, or whatever. Um, because when we do chemical reactions, we're not never going to be down at the really tiny square. In fact, we're not even really sure if this is exact. I mean, if this chemical reaction is exactly the way it looks. Okay, it starts out this way, it ends up this way, but we don't know what's going on down there. All we can do is look at what's happening in our real world. And what it means is we have one bunch of these, we'll need 6.5 bunch of these. We'll make 4 bunches of these and 5 bunches of these. So it doesn't matter if you use halves, thirds, quarters, etc., because they're just quantities. Okay, if you don't like, and I know there's some teachers say you can't have halves, and that's ridiculous, okay? Um, but if you don't like halves, it's real simple. You can just multiply everything by, to get rid of the halves, you just multiply everything by 2, and you get this. And it's exactly the same ratio. 2 to 13 is the same thing as 1 to 6.5. 2 to 8 is the same as 1 to 4. Okay. Okay, so that's the key thing here. So it doesn't matter that you have a half here at all. Okay. Okay, so now what we want to take a look at is, so when I was taking chemistry, I really didn't like chemistry for a really long time, almost until I started teaching it. One of the reasons I didn't like it because it's just like you're moving around numbers, you're doing math, you're memorizing stuff, and there doesn't seem to be any kind of real uh, stuff that makes you interest. Okay, and once I started thinking about chemistry and realized what makes chemistry take place, I liked it. Okay, so chemistry just became more than numbers and formulas and memorizing stuff. So, what we want to do is, why do chemical reactions take place? Yeah, why? And we want to start touching on the whys of chemical reactions with our combustion reactions here, because this is a really good place to understand why all chemical reactions take place. The main instigator in a combustion reaction is oxygen. It's the guy that makes the thing happen. So oxygen has this yearning, burning desire for electrons. It's really, really hungry. Yum, yum, yum. It's starving for electrons. And so what it does is it attacks other atoms so it can reduce its hunger. Okay? And it really does. Okay? It's really a hungry guy. And we'll go over why oxygen's hungry like that uh, when we get into atomic structure. Okay? And we'll find that that's out that there's some oxygen's one of the most hungriest atoms out there. There's only one other one, but every other element is sort of prey to oxygen. So what happens is oxygen attacks the alkane, and you could say it oxidizes it because it attacks it. Oxygen gets it, and so in this reaction, oxygen gets reduced. It its hunger gets reduced, and it does that by gaining electrons. It gets fed, while the alkane gets attacked by oxygen, and that means it's lost electrons. Okay, so this is a general scheme in all of chemistry, where one substance will be electron hungry like oxygen, and it will attack to get its hunger reduced, and the other substance will get oxidized, even if it's not oxygen, because the substance will behave like oxygen, and and the substance will lose electrons and be oxidized. Okay, so what we have is something's being oxidized and something's reduced. And when something's oxidized, it loses electrons, and when something's reduced, it gains electrons. And we have a couple of mnemonics that help us remember that. We have Leo, the lion, goes grrr. Okay, Leo, losing electrons, oxidize, grrr, gaining electrons, reduce. Or another way is oil rig. Okay, oxidized is losing electrons, reduced is gaining electrons. Okay, so oil rig and Leo. All right, turns out that every chemical reaction we encounter in our lives, unless you go to a nuclear power plant, will be of this ilk. That means kind. So what we call them is oxidation reduction reactions, or commonly called redox reactions. There will always be a substance that behaves like oxygen, gaining electrons or reduce, and another substance that behaves like the alkane and losing electrons. Okay, so we're finishing the combustion of alkanes, and so here's what you have to know. You have to be able to write the word and balance equation for all the 10 alkanes and explain what makes the chemical reaction take place in terms of oxidation reduction. We will go to the next slide will be single replacements. So there'll be two or three more slides for reactions, and so I'll go